Hi guys, let's begin our look at reactions of aromatics. Aromatic compounds, with the most common aromatic of course being benzene. But the reactions we see for benzene will apply to many similar aromatic systems. Now, aromatic chemistry is one of my favorite types of chemistry, inorganic, and I hope you enjoy it as much as I do. We have a warm-up here. You can take a look at chlorination of the aromatic ring. Looking at regiochemistry, is the chlorine going to end up in this position or this position? We'll learn about how to predict regiochemistry of such reactions. Okay, we have this handout. We also have the EAS handout. All right, there are three general reaction mechanisms for aromatics. One is EAS, electrophilic aromatic substitution. Here the ring is going to react with an electrophile. And we will focus on EAS reactions a good bit and here at the beginning. It's the most common mechanism that you will see for aromatics. But you also see two other mechanisms, and that includes nucleophilic aromatic substitution, or NAS, and there the ring acts as a nucleophile. I'm sorry, it reacts with a nucleophile. Hopefully I said the above correct. It reacts with an electrophile in an EAS. In NAS it reacts with a nucleophile. We'll see that. We also have the benzene mechanism. These are all essentially substitution mechanisms. All right, those two are labeled that. The benzene is also a substitution mechanism. In EAS, a hydrogen is typically replaced or substituted. I should have said typically. There are exceptions to many things we say. Is typically. And in the NAS and benzene mechanisms, a leaving group, a traditional leaving group, that is a non-hydrogen, is typically substituted. All right, that's just kind of a summary right now. We will see that, and you can refer back to that. EAS. Here are most of our EAS reactions, although a couple of them are not really EAS, but they're included here. We'll see halogenation of the ring. Again, we're replacing an H in each of these here. We can replace the H with a halogen, a sulfonic acid group, a nitro group, or a carbonyl group, most commonly a ketone group. All right. Now, a couple of extra reactions here. We will see that we can convert the ketone, we can essentially remove it. This is not exactly clear. Really what this is going to give is CH2R. We don't just lose this carbon. It becomes a CH2, and so the R group is made one carbon longer, and that's not clarified here. Or we can put an R group, a carbon group, on directly. Now with the nitro group, we'll see that we can subsequently reduce the nitro to the amino group, or the aniline. That's not an EAS. This is a sort of just a separate reaction that I'm showing here. And then the amino group can be replaced with various groups, including halogen. All right. At this point, just a summary. You will want to refer back to these. We'll begin by looking at the general EAS mechanism, including rate determining step. All right, and let's do that now on the other handout. We have a benzene ring here. We see the H. The H is going to be replaced by our electrophile. Okay. The ring reacts with an electrophile. Here it is here. Now the electrophile can have a formal positive charge or maybe not. All right, right here, not necessarily charged. This is just generic for some type of electrophile. In each reaction, we will clarify what the electrophile is, and in some cases, we'll have to generate the electrophile by doing chemistry with our reagents. So general line reaction here, and typically the H is going to be removed, or the ultimate fate of the H is to become H+, but again, that can vary. All right. So here's our benzene ring. We do have 3 carbon-carbon pi bonds. Now we know that those are fully delocalized, it's aromatic. But when we do mechanisms, it's best to consider an individual pi bond. And we can react this pi bond as if it is an alkene. And so our alkene chemistry that we learned in Organic 1 will be very applicable here. Of course, we know this is not just 3 alkenes, and that's the aromaticity story. All right. But we can, if we have an electrophile, these electrons can swing out and make bond to the electrophile. All right, we did this in Organic 1, right? Swing out, make bond to E, and that would leave this carbon as a carbocation. Right? It's nothing more different than taking this here, reacting it with H+. These electrons move here, and we're going to get bond to H and carbocation. Except here we have bond to something else, generic E+ here, carbocation. Now, this is called the sigma complex because we just made a sigma bond to the electrophile. And note that it's not aromatic because this carbon here now is sp3 and the ring is no longer a cyclic conjugated system. So there's 2 reasons why this intermediate is going to be particularly high in energy. First off, it's a carbocation. Second off, it's no longer aromatic compared to where we started. Now from here, we can theoretically do 2 different things. Just like here, if we had maybe Br- and we were reacting an alkene with HBr, we would do this, and then the Br- would attack here, and we would get our product that looks something like this, and we say we've added HBr to the alkene. Nucleophile attacks resulting carbocation. We would call this an addition. Overall, it's an addition reaction, but this particular step, the bromide is adding to the carbocation. We could do that here. If some type of nucleophile added to the carbocation, and I'm calling that base here, or some generic, it would now be bonded there. We would have done an overall addition reaction, but that does not typically happen with aromatics because this product would no longer be aromatic. Okay, not aromatic. Instead, we do a beta elimination step, and something takes the H that's there. Instead of the new electrophile, it takes the H, and if it takes the H, we can call it a base, and that's why this is labeled as B. So these electrons take the H, bond to the H. These electrons, these bonding electrons, move in to put that pi bond back in and to re-establish the aromaticity. All right. And the base now has taken the H. And so there's really only one intermediate here, and that's the sigma complex, the positively charged sigma complex. Rate determining step is forming that sigma complex, and then the beta elimination step to restore the aromaticity is considered a fast step. Now, very important, the sigma complex, while it's not aromatic, it is a resonance stabilized carbocation. And I show the resonance here, and it should be pretty familiar to you. Same thing. Okay, move electrons over. In organic 1, I called this the old windshield wiper. Move the electrons over, put pi bond here, leave cation there. Windshield wiper these down, leave cation there. And we have 3 resonance structures total. This one, the original, and 2 more, that's 3 total resonance structures. We can look at a resonance hybrid. It would look something like this. The electrons are delocalized over 5 carbons, but not that 6th carbon, because that carbon does not have a p orbital. And thus it is not a complete or a completely delocalized system. Now if we look at a reaction coordinate diagram, we have benzene. We have a transition state leading to our sigma complex. It's higher in energy because it's no longer aromatic. It's also a carbocation. From there, up here I showed 2 theoretical outcomes, an addition, and by the way, this doesn't clarify here, but this is not an addition. It is a substitution. We're replacing the H with an electrophile. And this is the substitution product. You see that it's lower in energy than the addition product because the addition product is no longer aromatic. All right, these 2 here, not aromatic. So if you consider that the transition state sort of mimics where we're going, a more stable product is going to have a lower transition state leading to it. Both of these would have the same sigma complex intermediate. But from there, we can go 2 different directions. And energy is not going to run uphill if it has a lower, an easier pathway. The easier pathway is to fall down and to give the substitution product. All right. Again, as I showed here in the notes, I take you back and refer to this here. We get addition. Alkenes typically give addition. Aromatics typically give substitution so they can remain aromatic. Okay. Now I have a question down here, and this question tends to be a little vague. But given 2 different EAS reactions, why would one occur faster than the other? You may think that's vague, or it may be pretty straightforward. The reason why one would occur faster than the other is because, well, you need to look at the rate determining steps. We would say because one sigma complex is more stable than the other. Now, this kind of assumes that we're coming from the same starting point. I could clarify this by saying of benzene, that would help clarify that. But basically, forming your sigma complex is the rate determining step. And it just depends on how stable is this sigma complex. That's really going to affect your rate. All right. If the sigma complex was, for example, much more stable, then the transition state leading to it would typically be lower, and this would be an easier reaction than going the other route. All right. Well, let's think about it. What can make sigma complexes more stable? The sigma complex is already resonance stabilized. Okay. So we can ask, even though it is resonance stabilized, how can we make this resonance stabilized carbocation even more stable? All right. And you can be thinking about that, keeping in mind it is a positive charge. And we will come back to that, sort of setting the stage for future discussion. All right. In the end, the EAS mechanism is pretty straightforward. It's just one intermediate, okay? Now let's look at specifics. The first specific we will look at is halogenation. All right. We see benzene reacting with bromine and a Lewis acid catalyst. Okay. Lewis acid catalyst. To get bromobenzene here. And if you balance this out, what's the fate of the other bromine? Well, it's HBr. Because don't we lose an H? It can team up with the other bromine. All right. Now, what is our electrophile here? Well, we got bromine. And bromine tends to be electrophilic, and alkenes will react with bromine. Yeah? Bromine is the electrophile. All right. It turns out that aromatics do not react as readily with bromine as an alkene because the electrons are delocalized here. But if we include a Lewis acid, such as FeBr3, we can make the bromine more electrophilic. And here, these electrons add to the iron. Okay? And these transition metals, such as iron or aluminum, not really classically a transition metal, but it still applies, they have empty d orbitals. And the empty d orbitals can be electrophilic. And lone pairs will add to them. All right? So we can say the iron is accepting a lone pair, and that's our classical definition of a Lewis acid. All right? So the FeBr3 Lewis acid, and this gives all right. That's 3 bonds to bromines. I'll just keep it condensed. But now this iron is minus, and this bromine is plus. Now we create a stronger dipole, a more permanent dipole here. This bromine is now going to pull electrons away. And it makes the N-bromine partial plus. All right, not a formal charge, but a partial plus as a result of polarization here. And this is your electrophile. Okay. We're not making Br plus. Not a single Br plus. Okay. Now these electrons will swing away. All right. We can consider either one the pi bonds. Swing away, attack here, and kick this off. This is almost like, well, how do you make oxygen a better leaving group? You protonate it, and that makes the oxygen positive, and then it will serve as a leaving group. Well, we're not using acid here to protonate a bromine. You typically never do that. Instead, we get a positive charge on this bromine by complexing it with a Lewis acid. Now it's more prone to leaving this bromine. Now the ring will attack this bromine and kick that off. When we do that, we get I assume I've hinged this up to make bond. So we hinged it up. All right. There's also an H there. Carbocation here. Got pi bonds there. Plus, we'll draw these out this time. That iron is now minus. We know it's minus because when it was bonded to 3 bonds, it was neutral. And it owned 3 electrons, but now it owns 4, so it's got an extra electron. Should be minus. Now here's our sigma complex that we showed on previous page. But over here, we did our mechanism with a generic E+. Over here, the electrophile was actually not a Br+, but it was this sort of complex here, and it was a terminal bromine, and we talked about how that was made to be electrophilic. Resonance stabilized. I'm not going to show resonance structures here. It's the same as the previous page. What's the next step? Something takes the H. Okay. This point, these electrons, it's sort of like a sigma bond acting as a base. These electrons break away from the iron. Okay. Usually how this is shown, the iron's like, okay, Br, I love you, but you're making me minus here. Take a hike. The Br takes a hike. The bonding electrons come over and bond to the H. These electrons move in, and that's going to give those two products. And when that Br left, we're back to Fe bonded to 3 bromines, and I'll just show it like that. And that's our catalyst reformed. The role of the catalyst was to make the bromine more electrophilic by complexing with it as a Lewis acid. You can also do this with chlorine, same exact mechanism, except if you're using chlorine, you probably want to keep your halogens consistent and use FeCl3. An alternative that's very common is aluminum tribromide or aluminum trichloride. You can actually just use the metal, either iron or aluminum metal, because once you combine these with the bromine, they will react with bromine to make the actual Lewis acid in situ. And so the actual metal is considered a pre-catalyst. Of course, you really only need one molecule. So 1 molecule of iron reacting with 1 molecule of bromine, you should still have plenty enough bromine around to do the reaction you need to do here. Okay? In the old days, chemists used to throw in like a piece of a nail, you know, nail and hammer, because it was metal. It was made out of iron. Because actually these something like FeBr3 is actually a little water sensitive, and may not be around in the lab. Okay. Either chlorine or bromine, they both work there with your Lewis acids. What about other halogens? If you try to iodinate a ring, you can do that. But you need to have an oxidant. You actually need to form I+. All right? Lewis acid complexation doesn't work with iodine. If you take elemental iodine, diatomic I2, and react with an oxidant, you can go to I+. All right. Oxidants that will do this include copper 2 chloride, hydrogen peroxide, or even periodic acid. Now, we don't have to look at a mechanism for the redox. It's probably a single electron transfer. But this is going to produce I+. That's what we're saying here. And once it produces I+, well, it's the same exact mechanism as shown over here where we showed E+. All right. And we can do a substitution reaction. Now, what about the other halogen, the other common halogen, fluorine? All right. Now, aromatics will react with fluorine directly. Problem is, it's too reactive. It's too exothermic. It may be explosive, and thus you typically need to stand back. All right. A little bit too dangerous of a reaction to try to use elemental fluorine. It's very exothermic because the FF bond is so weak and the resulting CF bond that we would be making is very strong. And so it leads to a very exothermic process. Now, there are some on the research lab, some so-called NF reagents, such as this here, where instead of using F2, you have an electrophilic fluorine bonded to some other type of atom. And here we have a positive nitrogen, and so the nucleophile attacks the F and kicks off that positive nitrogen. All right. For us, typically, we're not doing a direct fluorination. We will see instead where we can use a diazonium reaction. All right, to end up with a fluorine on the ring. And that was actually illustrated here. Okay, didn't say diazonium. A diazonium reaction is where we replace the amino group with some other group. And there it can be halogen, but here it can also include fluorine. All right? And we will see that later on. You'll also be doing a diazonium reaction in lab. It's one of the reactions of your aminofluorine. Okay. Let's see here. We had an outline here. Have we done everything on the outline? Halogenation, use of Lewis acid catalyst for chlorination or bromination. Need for oxidants when you do iodination to generate I+. Difficulty with doing a direct fluorination. Instead, we'll see a diazonium approach, an indirect approach to getting a fluorine on the ring. And then that brings us to nitration. All right. And nitration is the first reaction of the fluorine lab. And when you do a nitration of an aromatic, you typically use nitric acid. And the electrophile here is the so-called nitronium ion, NO2 plus. And here's a Lewis structure for the nitronium ion. And we see with the positive charge here, it should be electrophilic. Now here's a Lewis structure for the nitro group, such as coming off of the benzene ring here. It's always going to have two charges. The NO2 group, it's net neutral. Okay? It's somewhat analogous to a, well, if that was an H, it'd be a carboxylic acid. But if we consider this to be an anion here, this would look like this. That's net minus. But if for some reason, if this atom could be positive, all right, then the whole thing would be net neutral. And indeed, if that's a nitrogen, it is positive. And so the entire group is neutral. And so we just say NO2 as a condensed form. Okay, so the nitronium ion is our electrophile, but we need to know how to form the nitronium ion. Now, nitric acid has a Lewis structure that looks like this. HNO3. And you see, to get to the nitronium ion, what do we need to lose? We need to lose an oxygen. The oxygen here, the OH group, needs to leave. How do you make OH a better leaving group? You protonate it, and that's why we typically use an H plus catalyst here. And the first step in this mechanism is to react nitric acid with an acid. That's kind of odd. Don't forget charges over here, okay? Here the nitric acid is acting as a base. That's crazy, a strong acid acting as a base. Now the most common H plus catalyst here is actually sulfuric acid, which is actually stronger than nitric acid. Now, don't tell anybody I told you this, but it is possible for nitric acid to protonate itself. That is, one molecule of nitric acid acting as the base, and it taking the H from another molecule of nitric acid, which, as we know, is a strong acid. So you don't always need sulfuric acid. But in practice, adding the sulfuric acid does catalyze the reaction and make it a faster reaction. But sometimes you may not want it to be a faster reaction. So we can talk about that more. Protonate the OH, get here. Now this can leave, and we can do that two different ways. I'm actually going to kind of, our old-fashioned, if we can make a pi bond, if we can use a long pair, make a pi bond, and kick off a leaving group. That's always easy to do, right? And what does this arrow movement give? It gives the nitronium ion plus water. Yeah? And I'll redraw it here. Now that the nitronium ion is formed, now these electrons will attack the nitrogen. Now nitrogen can't have 5 bonds. And we push electrons back onto one of the oxygens. And that gives, okay, this is our electrophile. That gives our sigma complex. Bond to nitrogen, double bond to oxygen on one side remaining, the other is single bond to oxygen. That oxygen now has 3 lone pairs and a minus charge. The nitrogen is still positive, even though electrons attacked it, still positive if you look at it, and that is actually the nitro group. And of course we had here, it's our sigma complex, resonance stabilized. You should be able to show resonance structures if asked. And now something takes the H. Well, what was a minus here? We had H+. Let's say the minus was the bisulfate anion. These electrons take the H. These electrons move in to restore the aromaticity. We get that product, and we reform our catalyst. Of course, we could have used water to take the H, and then we would have reformed H3O+, but that's how sulfuric acid exists anyway, because it's an aqueous acid. Okay, nitration is actually a very common reaction of aromatics. Nitro groups, you most often see them on aromatic rings. But not always. There's a couple of examples where nitro groups on alkyl type compounds. Nitroglycerin would be an example. Of course, in nitroglycerin, the nitro groups are actually bonded to an oxygen, and they're sort of nitrate esters. The most simplest is nitromethane. Okay, we'll draw the CH3s like this. Nitromethane is a molecule that's known. It's actually a solvent, sometimes used in the lab, but it's pretty rare. Pretty rarely used. It's much more common to use the CH3CN, and that looks ugly. Usually it's going to be like this or like this. That's acetonitrile. Much more common than nitromethane. And we'll actually use acetonitrile during the Organic 2 lab. I've only once or twice ever used nitromethane in my chemistry career. Okay, now the nitro group is the most common precursor to the amino group. Once you get the nitro on, you can reduce the nitrogen to the amine. And this is thus a 2-step route to aniline type compounds. All right, this is an aniline. That's aniline itself. If we had substituents, it would be a substituted aniline. Or if this is another aromatic ring, it would just be called an aromatic amine or something. This is done a couple of different ways. One is with some type of active metal, such as iron, tin, or zinc. Usually these are base metals, and acid, in the presence of acid. And this is called a dissolving metal reduction. Okay? And the metal gets oxidized and the nitro group gets reduced. For example, if you use iron, it will be oxidized to iron 2+. Now in Gen Chem, you may have seen a reaction where metals will react with acid to form hydrogen gas. Okay? And here, the iron is getting oxidized and the H+ is getting reduced to the elemental form. So we see the metal serving as a reducing agent here. It will also reduce nitro groups, and the H's will end up on the nitrogen. We're not going to look at a mechanism here. It's probably a radical reaction. No mechanism. All right. It's called dissolving metal reduction because you start out with the metal, it's not dissolved, because metals typically do not dissolve in any solvent. But as it reacts and it becomes the ion form, it then dissolves. The problem is sometimes these things will form insoluble salts, and it may not really be dissolved. It depends on the conditions. And there's a variety of other factors. Because it's under acidic conditions, you typically need to basify this during workup. And once you basify it, you can get things formed like iron hydroxide. And once these metals complex with hydroxide, they tend to no longer be soluble. And you have to filter them out. Okay? We'll talk about that as needed in lab. Now, what acid is used here? Sulfuric acid. You can even use acetic acid sometimes. It's a weaker acid, but sometimes it'll work. HCl. You can even use acid salts such as ammonium chloride, which would be considered an acidic salt because it's a weak base and a strong acid combined. Now, another way to reduce the nitro group to the amino group is using hydrogen gas. If you remember from Organic 1, we used hydrogenation to reduce an alkyne or an alkene. All right. Hydrogenation will also reduce a nitro group to the amino group. And the fate of the oxygens there is formation of water. That's also the fate of the oxygen when you do a dissolving metal reduction, most likely. That's what happens to the oxygens. Okay, so we showed that here. Nitration followed by reduction to give the amine. All right. Now let's finish up this video by looking at sulfonation. If you take an aromatic, here benzene, react it with sulfur trioxide in the presence of sulfuric acid, we can get the sulfonic acid group on the benzene ring. Here's your Lewis structure for the sulfonic acid, and this is called benzene sulfonic acid. Similar to a carboxylic acid, but sulfur, and then the sulfur has two oxygens bonded to it. And you see the charge here of the sulfur is neutral. It's owning 6 electrons. All right. Now, sulfonic acids are not that common. Certainly not as common as like a nitro group, but we still cover them. We'll also make some miscellaneous comments about sulfonic acids. Okay, here you have SO3. We could draw a Lewis structure like that. If we protonate one of these oxygens, we can get a Lewis structure that looks like this. Now, by the way, I showed an expanded octet. 1, 2, 3, 4. No, I didn't. 6 electrons around sulfur. Here. Now, if I show a resonance structure, this oxygen's pulling. If I move electrons here, I will then get, I'm going to draw it over here, resonance structure that looks like that there. And now I have a positive on the sulfur. Resonance structure of this. So I didn't protonate the sulfur and make it positive. I got the sulfur positive by protonating an oxygen and then considering a resonance structure. Now this is the electrophile. These electrons break away, attack here. That's going to give bond to sulfur. The 2 double bonds remain and the OH remains. Because sulfur can expand its octet, we're just making a bond to sulfur. The H is there. Pi bonds remain here, positive here. Resonance stabilized sigma complex. We see the sulfonic acid group is right there intact. And then something can take the H, okay? Just like above, I'll use the bisulfate anion. These electrons take the H, these electrons move in, restore the aromaticity, and we get our product. And we reform H2SO4. Okay, so it was again catalyst. Now, something unique about this reaction is it is reversible. Okay, this is H+. If the ring reacted with H+, could we come back here? Yes. And if we came back here, we could come this way. All right? You need to think about it. You need to, and if we show that going forwards, we would start with benzene sulfonic acid, heat it with an H+ catalyst, and you can actually get back to benzene and SO3. Okay, you should provide a mechanism for that on your own. It's really just the opposite, but looking at it on your separate from that would be helpful. So sulfonation is reversible. And if you go in reverse, it's really an EAS reaction. But going in reverse, the SO3 is replaced. Remember, that's why over here I said in EAS a hydrogen is replaced. Well, not always. Sometimes something else other than hydrogen could be replaced in an EAS. All right. And later on, we may talk about this when we refer to protecting groups. And the sulfonic acid group may serve as a protecting group, which you can put on the ring, and then you can take it off later. Protect, deprotect. Okay. I'll end this video here. We're going to next get into substituent effects. Okay? Because thus far we've been reacting benzene. And if you react benzene, all 6 carbons are the same. It doesn't matter where we put the new group, it's going to be benzene sulfonic acid. But what if you react, for example, nitrobenzene? What if you tried to brominate it? Would the bromine go next to the nitro, ortho? Would the bromine go 2 away, meta? Or would it go 3 away, para? Okay, that's regiochemistry. All right, and that's going to be, that's going to fall under substituent effects. What is the effect of the nitro group in directing the regiochemistry of a newly added group? Also, will nitrobenzene be more reactive or less reactive compared to something like just like benzene? That again will be a substituent effect. How does a current substituent affect reactivity of the ring? Okay, we'll pick up there in the next video.